So, welcome back to the lecture series of electronics, measurement and instrumentation. In this lecture, I am going to discuss about emitter follower as a voltmeter. See, that is this particular circuit is used as a emitter follower. So the first question, why it is called the emitter follower? Because the output of this circuit is taken from the emitter. See this diagram, actually the IE is the output current that is flowing through a emitter. We know that basically this particular combination, this pointer and this RM, this combination is a de-Arsenal movement or PMMC instruments, and it's used for the measurement of the current. To convert it into the voltmeter, we use a series resistance RS. Then to convert it for the measurement of low and high voltages, we connect a emitter circuit. So we are using this emitter follower because output here is follow the input, and we have applied the voltage that we want to measure at input of the terminal. So this particular emitter follower circuit does not amplify the applied input, so that our input signal will not be the change. So that's why this circuit is called the emitter follower, because it follow input. Output is always follow input, and second, it's offer a high input resistance and a low output resistance. So once it is offer a high input resistance, it means whatever voltage applied at input terminal is transferred to the circuit, and it's offer low output resistance, so it will not modify resistance of the output. So overall this particular circuit combination circuit will not change, and we required a circuit that offer high input impedance and low output impedance, that this particular circuit will also offer. And then it's also work as an emitter follower, so its output always follow the input, so our measurement will not disturb. It means with help of this circuit, without disturbing our measuring quantity, we are able to measure this particular quantity. So this emitter follower offer high input resistance. It is basically properties of emitter follower, and low output resistance, that already I explained. The basic emitter follower voltmeter circuit is shown in this figure, in which PMMC instrument and multiplier resistor. I have already explained this PMMC instruments. It means a pointer, this where I am writing 1 ampere and this RM. Actually it works as an emitter, and we have connected a series resistance RS, so that this particular emitter is converted into a voltmeter. So that is overall the circuit, and that they try to explain in this explanation. The DC supply is connected as positive terminal to the collector of the transistor, and negative terminal is connected to the deflection meter. See this particular diagram, that is a negative terminal, and that is our deflection meter. So the negative terminal is connected to a deflection meter, and similarly the positive terminal of the voltage is connected to the input. So that's all about the PMMC instrument. Then from this circuit, the transistor base IB is substantially lower than the meter current IM. It means actually the base current IB is small in comparison to the IM. That's why this particular IE is equal to IM. If the base is large, then this relation is not possible. So we use an assumption that the base current is lower than the meter current. Then the IB equal to IM upon HFE. HFE beta, you know that it is a common base parameters, and it is actually called the current gain. So therefore the circuit input resistance is E upon IB, which is much larger than the circuit resistance. Why it is E upon IB is much larger? Because HFE is large, so IB is small, That's why Ri equal to E upon Ib. So Ib is small, it means Ei is large. So that's all about the trick. Then we understand this whole concept with a particular example. In this example, actually, see this, a simple circuit follower that is shown in the figure, in the previous figure itself. VCC 20 volt, RS and RM that is equal to 9.3 kilo ohm, IM equal to 1 M. And then FSD is nothing but the full scale deflection. And the transistor HFE is 100. I am already explained the HFE is a current gain that is large. So see here HFE is 100 is a large quantity. Calculate the meter current when E is equal to 10 volt. Determine voltmeter input resistance with and without the transistor. So this particular diagram, see this VBE. What is the value of VB? It is nothing but VB minus, because VB is potential difference. So VB minus VE. See this circuit. So VBE that is equal to VB minus VE. So what is the VE? VE is given even, and what is the VB? VB is this particular voltage. Then it means VB equal to VB minus VE, it means E minus VE. It means VE, because we want to calculate actually VE. Why we want to calculate the VE? Because this particular VE is applied across this voltmeter terminal. Then VE equal to E minus VBE, and in the question given E equal to 10 volt and VB equal to 0.7 volt. When in the case of transistor, if you consider that transistor is on, then the VB is 0.7 volt. This value is a standard value, and I hope you people are remember. Again, I remind you that VBE is based to emitter voltage, and its value is equal to 0.7 volt when we consider a particular transistor is on. So it is 0.7 volt, it means we have calculated the VE. Then the IM equal to VE upon RS upon RM. RS upon RM is given 9.3 kilo ohm, and it is equal to 9.3 kilo. See the IM equal to 1 milliampere, IM. And if IM is 1 milliampere, so we assume that what is the value of RI. So if IM is 1 milliampere, IB equal to 1 milliampere divided by 100, then it's become 10 microampere. And if it is 10 microampere, so see here RI is equal to 1 mega ohm. So it means input resistance without the transistor, it is equal to 9.3 kilo ohm, and with the transistor it's become 1 ohm. So see the transformation from 9.3 kilo ohm to 1 ohm. It means sufficiently high input impedance is achieved with the help of emitter follower circuit. So this transistor based emitter follower introduce an error in a simple circuit follower. For example, see here, this particular circuit have the advantage, but there is some disadvantage. So we discuss this disadvantage. If E equal to 5 volt, then the meter should read half of the FSD, but actually it reads 0.46. See here, if it is the 5 volt, then the actually what we theoretically calculate, it is 0.5 full scale deflection. That is 0.5 milliampere, but actual reading, if we have practically measured it, it's come 0.46 milliampere. It means there are its particular emitter follower circuit introduced error in the measurement. This error can be eliminated by using a potential divider and additional emitter follower. This particular circuit to remove this error, so that its actual reading and our theoretical reading both should match, or error will not introduce in the circuit. So we use this particular circuit. See, in this circuit we are using two transistors. Both can work as a emitter follower, and again in the between these two transistors we connect this voltmeter circuit, DC voltmeter circuit. See this circuit, it is a voltmeter circuit, and there are two resistance. So, and this particular resistance consists of a potential divider bias. There one resistance, it is a simple base emitter voltage, and see here this if you see this previous diagram and this diagram, actually both are the same. Only see here, only we are, instead of placing this circuit like this, we place like this, and this is connected to a circuit. See this terminal is connected to this terminal, and here instead of this we using this circuit. So it is a potential, and that particular circuit is called potential divider circuitry. So this practical emitter follower circuit use a plus and minus or dual polarity supply. See here, it uses plus VCC and minus VCC. That is called the dual power supply. There is a lot of advantages of using the dual power supply. So in this particular circuitry, we does not require a common ground. So this particular circuit, this voltage is dropped. So actually this ground is just for sake of representation. So here, see here, this, in normal this is a grounded terminal, but here it is a minus VEE terminal, and this terminal is the plus VE terminal. So this is called a dual voltage supply, and is used to replace the ground. And there are a lot of advantages that is associated with this circuitry. In the analog electronics, you will study about what are the advantages of using dual power supply. So here the transistor Q1 has its base bias to ground via the resistor R1. See here, this is the resistance R1, and a potential divider R4, R5, R6, R4, R5, R6 provide adjustable bias voltage VP. It means with the help of this three, I am able to vary this VP voltage. And this particular VP voltage is actually applied to the base of this second transistor, that is denoted as Q2. So the resistance R2 and R3 connect to the emitter terminal to negative supply voltage, and the meter circuit is connected between the transistor emitter. This already clear. The circuit input resistance is R1 in parallel with the input resistance of the transistor base. So this is R1, and it is the parallel with of the input resistance of this particular circuit. So when no input voltage is applied, so E is equal to 0. So see here, initially this particular E is equal to 0. So it means there is no voltage is applied. So once it is no voltage is applied, E equal to 0, the base of Q2 is adjusted to 0, adjusted to give 0 meter reading. And at this point of the time, we adjusted this particular circuit in a such that this meter indicate once E is 0, then this meter indicates 0. It means this particular circuit is balanced, or we call it, we adjusted this particular circuit in such a that when E is 0, meter reading is 0. So now suppose a 5 volt input is applied to the base of Q1. Q1, it means the previous transistor 1. Then VE1 minus VE1 minus VE2 equal to, that is equal to basically E1 is E and VE2 is VE. Sorry, VE1 is equal to VE minus VB1. I'm already explained, and this VE2 is equal to V. So that is equal to 5 volt. So thus, unlike the case of simple emitter follower voltmeter, all the voltage to be measured appear across the meter circuit. No part of it's lost in VBE. It means voltage VBE terminal, it means potential drop across the terminal that denoted as VBE, base to emitter terminal, is removed in this particular case. Again, see this particular diagram, that is actually V. So it is VE1, VE2, so V is equal to, they are writing VE1 minus VE2. So VE1, it is the emitter voltage of this, so it is VB minus VE. So here we can put VE minus VBE. Similarly, this VE2 is equal to VE2. VE, because the both Q1 and Q2 are the common. So in that way, if we apply the 5 volts, it's become 5 volts. It's not converted into 4.3 volt. So that is the basically advantage of this particular circuit. That's again they using a particular example. In this example, things is very clear to you, and in this particular example, just we put the value of VCC equal to plus minus 2 volt, R2 equal to 3.9, and we need to determine what is the value of I2, I3 when E equal to 0. And similarly, VE equal to 1 volt and 0.5 volt. So the case A, when E equal to 0, then VR1 minus VR2. VR2 minus VR equal to VR3 equal to 0 minus VV. This the previous example it is given, it means V is equal to 11.3. Once we know this value 11.3, I am able to calculate the I2 VR2 upon R2. So similarly, if E equal to 1, we can again using the same formula, we calculate the value of I2. See here it is this, then it is 1 volt, V is 0.4, then this, it means V is equal to Vp minus this. So V equal to this, and it is around the 0.5 volt. So in this basis, we are able to calculate all these value. Then again the question arises how to change the range of the voltmeter. So just for the changing range of this voltmeter, or to convert its multi-range voltmeter, we are using a different resistance value. So instead of the one resistance, we use RA, RB, RC and so on. So that is called basically volt change of the volt resistance circuit. So that is all about the today's circuit. Then in the next class we are going to discuss about how to implement a multi-range voltmeter circuit. Thank you for your attention.